Good evening, everybody. All right, what I want to talk about is involving Chapter 6 in your PSAT textbook, which deals with scatter plots and the exponential equation. I'm skipping over the whole scatter plot thing, though send me an email if that's something you want to talk about. But what I want to focus on is the exponential equation, the growth and decay thing. Okay, so in your text, what they do is they're going to give you this linear equation, right? And you can think of this as the y equals mx plus b function. So I'm just going to skip over that. Everybody seemed to be okay with this. But again, send me an email if this is something you want to talk about. But let's talk about this thing right here. The exponential equation, right? Where we have y equals x sub 0 times 1 plus r raised to the x power. Okay. What this means is, let's just break this down. This means our result is equal to what we started with, which is all that the x sub 0 or x naught, as your textbook will say, means, times whatever our rate is, which is written as a parentheses 1 plus r, raised to the exponent of however many times that we are dealing with something. So for example, let me give you an example. The question might be, well, how many things would we have? So y, right? What would be our result if we started with 100 bacteria cells and they were growing at a rate of, say, 50%, and we calculated that for 5 periods? So we would just plug everything in, right? We start with 100, we plug in 50% over here, and then we raise it to the 5th power because we were calculating 5 different cycles. Okay. This looks confusing, but it's actually fairly straightforward. Let's look at a couple of problems just to illustrate this. So, for example, skip over this, but look at this. Okay, so we start with a group of 512 fencers entered a tournament in which half the fencers are eliminated in each round. Which of the following represents the number of fencers left as a function of the number of rounds? Okay, so let's not freak out over this. Let's plug in what we have. So I'm going to pull up, pull up Paint, and let's see what we got. Okay, so remember our basic equation is this. Wrong thing. Let's try that again. Okay, ignore that. Let's do green. Okay, so here's what we have. So the total number of things is equal to whatever it is that we started with times whatever our rate is, which we always start with 1 plus whatever the change is, raised to some sort of power. Okay? So they said that, we can cycle back to the text here, is that we started with 512, and then the rate seems that a half of them are eliminated every single round. Right? So that means we're going to go down by 1/2. So all we have to do to write that, let's change the color, is going to be the total number of fencers that we have is going to be equal to, well, we started with 512, so we write that down, and then the rate. Okay, the rate is we start with 1, and then we indicate what's the change. So the change is we went down by 1/2, so that would just mean we subtract 1/2, right? And then to however many cycles that we're calculating. Good? So then, okay, then that would mean that the total number that we have is going to be equal to 512 times, well, 1 minus 1/2 is just 1/2, right? Hopefully. And then that raised to the x power. Okay, well then which of these answer choices would fit? Let's look at this for a second. Okay, well, hopefully you can see A doesn't work, right? 512 minus 2x, that doesn't fit. And then we got, well, the only two things that we have that have 512 in them are B and C. Let's see if we can simplify things a little bit further using our exponential rules. Okay? But hopefully everybody's okay with this that I got right here. If you need to, pause the recording and then check it. But hopefully you're okay with this. All right. But, so here's what we would do. We could say, well, using our exponential rules, just draw a little arrow over here, 1/2 raised to the x power. Remember, when you have an exponent raised to some sort of fraction, it's really just the exponent being attached to each of those things. So really, essentially, I could say that's the same thing as 1 to the x and over 2 to the x. And again, we don't know what x is, right, because they didn't tell us how many cycles we were counting, but we just, we're just basically simplifying this expression. Okay, well, then think about this. What's 1 to the x? Well, 1 to any power is always just going to be 1. So we really basically have 512 times 1 to the x over 2 to the x. Okay? Well, again, 1 to anything is always going to be just 1. So it basically works out to being 512 times 1 and then over 2 to the x. Now, that's basically all that we can do, is say that that would be our result. And of course, let's see, that would match up with, that would have to be answer choice B. Okay? But again, kind of the idea here is we just plug in whatever variables that we know into our equation and just simplify as best as possible. So in this case, we knew what we started with, right? We knew we started with 512. We knew the rate was it went down by 1/2, so that gave us ultimate rate of 1 minus 1/2 is just going to be 1/2. And then what we were trying to figure out was what the ultimate result would be given that this remained unsolved for. So all we had to do is just basically simplify as best as possible using the x in our equation there. I think I just made that sound worse. I'm sorry if I did, but hopefully this makes sense to you. If not, again, email me. You know how to reach me, and I will elaborate further. But okay, so let's go ahead and do quickly the next problem. Let's look at this one. This one is a little bit more obnoxious. Okay, so I'm skipping over scatterplot modeling, like what the graphs look like. Let's just keep on with the same topic of how do we deal with these exponential equations. So scrolling down, where are we getting? We got something here. Hold on a second. Okay, this is the obnoxious one. Okay, here's a chance to try a multi-part question involving a scatterplot. Okay, so questions 5 and 6, we have to use the same information. Okay. And it says, the scatter plot shows a portion of a uranium sample's radioactive decay. Keyword, decay. We know that that's going to mean one of those exponential equations, right? We have some sort of change exponentially because it's decaying. It's not decreasing at the same rate every single time. There we go. Erase that. So we know that we're going to have to deal with something that involves... Let's do red again. Something that involves y equals some initial value times our rate change raised to some sort of time structure, right? How many cycles are we dealing with? Okay, but again, kind of the key takeaway here is that the word decay is going to indicate that this is what we need to do, right? So let's look at this. How many grams of uranium were in the original sample? So let's think about what we can plug in. This chart is giving us a y value right here, right, and an x value in terms of number of half-lives, so that's referring to the time, how many decay cycles we're talking about that we're measuring. And what could we match up? Well, we can just pick something right on an easy axis, right? We know that when the number of half-lives or the number of time cycles is 4, that matches up with this point right here on the y-axis. And again, pause the video if you need to, but we should see hopefully that this is midway between 7.5 and 5, so that would just simply be 6.25. So let's plug this in. Okay, so we know that when y is equal to 6.25, we don't know what we started with, so we leave that go. But again, it said half-life, right? So that means we're going down by a half, and our cycle is 4. So that simplifies to just simply being 6.25 is the same thing as whatever we started with. Well, 1 minus 1/2, the decay is a half, so that's just going to be a half raised to the 4th power. Well, you can pull up your calculator on this, or you can just trust me as your instructor. always a dangerous thing to do. Never, never trust your instructor. But I did, in fact, do the calculation ahead of time, and that gives us, because I can't figure out what that is in my head. I don't know. Okay, so whatever whatever we started with is equal to that times 0.0625. Again, just check this, right? Just plug in 1/2, raise it to the 4th power in your calculator and see what you get. But you should get this thing. Otherwise, your calculator's probably broken. Okay, so then at that point, then what we do is we would just, remember, we're trying to figure out what we started with, this thing. So I want to know what is x naught or x sub 0. I just divide both sides by that, right? That's all we got to do. Plug that in. Okay, and then again, you can check your calculator. Ta-da! Right there. See the answer, right? I plugged it in previously. There it is. But yes, the answer is 100. And we're talking about grams, so in terms of science, let's put that down. But 100 grams would be the answer to that problem. Okay, so again, just kind of as a recap, here's what I want you to take away from this. If presuming that you stayed through it through the entire ordeal here. But the idea is, all we have is, there we go again. We have our basic equation is whatever our result is equal to whatever we started with times the rate, and that rate is raised to some kind of power. And the power just indicates the number of times that we were doing this cycle, right? If we were cutting everything by half every single time, it would just mean we would, however many times that we were doing it, that would be the number that we would put for t. Okay? All you have to do with these sorts of equations is plug in what you know, right? They'll always tell you enough. Like, look at this. We have 1, 2, 3, 4 variables, right? They'll always give you 3 of them in order to figure out the missing one. So if they want you to figure out what you started with, they will tell you this, that, and that. Okay? And all you have to do is just plug in the stuff into the equation and then use your basic algebraic principles and solve for the missing variable, right? Okay. And again, with risk of being redundant, if we wanted to figure out this one, well, then they're going to tell you that, this, and that. Plug in what you know, simplify, and then solve. Hopefully this was helpful. If not, go ahead and send me an outraged email, and I will give you some more information and examples and tailor things to what you need. But anyway, have a good rest of your evening, day, or morning, depending on when you are watching this.